Syzygy, Episode 7, Plumes of Ice on Europa. Welcome to another episode of Syzygy. In this particular edition, we're talking about something very, very cool, actually quite cold, out in the solar system on Europa, which is one of the moons of Jupiter. It's been confirmed this week, just a week ago this paper came out, about ice plumes coming off the surface of Europa. Now, this is really interesting because A, we kind of thought they might be there, and now we're pretty sure we do. And the information for that was buried in some data from a mission many years ago. So we'll be talking about that. But B, also, that this is really tantalizing about the search for life out there in space. If you can find water, maybe you can find signs of early stages of life. So we're going to be talking about that. Joining me on the microphone, as ever, Dr Emily Brunsden. Hi, Emily.
Hello, hello.
Now, before we do get into the moons of Jupiter and water thereon, a little bit of TESS update. We've got first light.
Yeah, we got a first picture. It's
excellent.
So exciting.
Now, this is the Transiting Exoplanet Survey satellite. This is the little telescope that was launched, about a month ago
Yeah,
or so?
just about,
which is very exciting because it's doing all sorts of interesting stuff, not only about exoplanets, but also about Emily's favourite subject, which is starquakes, looking at variable stars. And so we're here in the Syzygy studios. We're very excited about TESS. It's very, very cool. And so we'll be bringing you play-by-play of everything that happens to TESS. But this one's particularly cool because it's gone through all of its positioning maneuvers. It's tested out its cameras and it's taken us for its first real picture and sent it back to us. And what's it a picture of?
Stars.
Stars. Lots of stars,
Lots
right?
and lots of
We'll
stars.
put a link to it in the show notes.
Yeah.
But I mean, you look at this and it really does make you realise we don't see anything from down here on the Earth's surface. There's a lot of stars out there.
It's a totally gorgeous image in its own right, and it's just a test.
Yeah.
I've put it as my backgrounds, and all my devices have now got this gorgeous background on them.
Can I just say, I think you're a little bit obsessed by this.
Maybe.
You're a TESS obsessive.
Test
All right. Well, go Tess. I think that's awesome. Well done. The camera's working. Now start taking some serious data so that Emily can get busy. So on to topic of the day, which is Europa. Emily, take us through this. What's been going on? This is really new, isn't it?
It's so exciting. So this is a Nature paper that came out last week.
Mm-hmm.
It was published by, and I'm really sorry if I get this pronunciation wrong, Syzygy from the University of Michigan and the collaborators. And what they found was they dug down into some old data from the Galileo mission and managed to find evidence that the Galileo space probe actually flew through an icy plume on the surface of Europa.
Now, Galileo mission, when are we talking here? When did this happen?
So the mission itself, it was launched, wait for it, way back in 1989.
Goodness, 1989. So that's the year that I turned 18. That's how old I am. But 1989, that's...
I hadn't even made it to school.
Yeah, you weren't even at school. God, that makes me feel old. That's a long time ago. But of course, it takes a long time to get out to Jupiter.
Yeah.
So when did the mission actually start having a bit of a poke around the moons of Jupiter?
Yeah, well, it poked around Jupiter starting from 1995 to up until about 2003, so about 8 years. And in that mission, it visited Europa. So Jupiter has 4 Galilean moons. These are actually the 4 brightest moons that we can see. So they were discovered by Galileo when he peered at Jupiter with his telescope.
How many moons has Jupiter got in all? It's got a lot.
More than 60. Yeah, lots.
Yeah,
lots and lots.
But a couple of big ones, 4 big ones.
Yeah, these are the big bright ones that are quite close to Jupiter. So there's 4 of them. This is the second one out from Jupiter itself, Europa. And the Galileo spacecraft flew by something like 11 times. And in one of those flybys, it turns out that it probably passed through this icy plume, and there's data to show the recording of that plume.
So what we're talking about here is a moon, and just for comparison, like roughly how big is this thing? Is it the size of our moon? Is it bigger? Is it smaller?
Just a little bit smaller.
Right,
So,
right, but comparable to our moon, right?
Yeah.
And coming from the surface, we're pretty sure, are these jets, these geysers of water
Yeah, they have a cool
jetting off
name.
into space.
Cool name, cryovolcanoes.
Very nice. Oh, I like that.
Yeah.
That's cool. That's even better than icy cold Jupiter moon geyser thing. Cryovolcanoes.
Yeah. Well, it's interesting. So the cryo plumes, definitely, they're not really volcanoes in the sense that you get volcanism on the surface of the Earth. There's not, lava coming up, and it's not this big buildup of pressure underneath the surface. Well, actually, that might not be true. It kind of is a bit of a buildup of pressure, and then you get this water and ice escaping from the surface of the moon up into the atmosphere.
Okay, so back in the sort of late 90s, maybe early 2000s, the Galileo mission was wandering around, taking pictures of Jupiter, having a good look at some of these moons, and pretty sure that it wandered through one of these jets. Didn't know it at the time.
No,
They didn't do this intentionally.
They weren't actually looking for these plumes at the time. The probe was doing things like measuring the magnetic field strength of the moon. It was looking at plasma, so looking at charged particles that were around the moon, and trying to understand how those particles interacted with Jupiter's magnetic field, which is really strong. And we didn't know really about these cryovolcanoes at that point. In fact, we only discovered them on another moon in our solar system in around about 2005.
Right, and what was that?
That was Enceladus, which is a moon of Saturn.
Right. And so it's got water plumes doing the same kind of thing. And how were they discovered?
That was a Cassini spacecraft.
Right.
Yeah,
right.
So Cassini just did fabulous things for Saturn generally, and we learned so much. And this was just one of the amazing discoveries they had.
Okay, so I've got a couple of questions. All right, so first of all, why is this news now? I mean, this paper was published last week, but we're talking about a mission which was 20 years ago.
Yeah.
So why is this news now?
So this is a wonderful story in science, I think. You have a huge amount of data that was collected for a particular purpose. It was analysed, it was published and so on. They learned a lot about the magnetic fields of Europa from the Galileo spacecraft. And then the story goes that some of these space scientists were at a different presentation looking at some Hubble data from Europa.
This is recently.
Very recently, yeah. And they were inspired and thought, well, actually, we've been to Europa. We've had a probe fly around. I wonder if there's anything in the data that can tell us about these icy plumes.
Now, what you're talking about with the Hubble thing, because the Hubble Space Telescope, which, lots of people have seen these amazing pictures that Hubble has taken of the universe, galaxies far, far away and so on. But it actually, if you train it on Jupiter or on the moons of Jupiter, it can actually easily look at those as well. It'll happily look at pretty much anything you throw at it. And they had taken some pictures still quite some time ago, a number of years ago, of Europa, which showed these plumes, or at least seemed to show some plumes, because it was still a bit fuzzy, wasn't it?
Yeah, so even the Hubble Space Telescope doesn't have the resolution to really drill down into the atmosphere of Europa. But in 2012 and 2016, they saw what could be these kind of bright smudges appearing around the surface, which were then put down to be these ice volcanoes coming up.
Okay, so it's looking like it probably is. But as you say, these other scientists who had worked with the Galileo mission and had the data from the Galileo mission many years before looked at that and went, well, we should have data about that, maybe. But buried in our data that we've sort of, got on a shelf back in storage somewhere from that mission, we should go and have a look at that.
And the wonderful thing is, in the 20 years since that mission, we have been able to develop much, much more rigorous models that can actually produce the effects that we would be able to measure with the spacecraft that wasn't actually 100% designed to measure these things.
Yeah, because that's the really cool thing, isn't it? Is that Galileo was not sent up there to look for these things. It wasn't expecting to wander through them and take measurements, but the tantalizing possibility that data is sitting there saying, if you look at this the right way, it's all waiting for you. Here are these plumes. So I'm assuming they found them.
Yes. So specifically what they were looking at in the data were the magnetic field strengths, and they saw these sharp changes in the magnetic field when the flyby happened. Now, this is a really interesting flyby. It's actually the closest that Galileo ever got to Europa. and it got to maybe, well, at least within 400 kilometres of the surface, anything between 400 and 200 kilometres, somewhere in that region, which is kind of the top limit of where we expect to find evidence for these geysers.
But even so, I mean, that's a long way up.
Yeah.
You know, geysers on Earth aren't getting anywhere near them. Maybe, 20 metres on a really good day. But the fact that I'm assuming Europa doesn't have much of an atmosphere, if anything, then these things shoot a long way.
Yeah,
long way up.
Yeah, and I'm also looking at very, very small changes in the atmosphere. So you're basically looking for a little disturbance that the geyser has caused in the upper atmosphere.
So, okay, these have been found in this old data, which is very cool, and that's an awesome story of the fact that we have so much data sitting there from so many astronomical surveys and missions and so on. And we might come back to that in a little bit and have a bit more of a discussion of that, because that's really interesting. But secondly, so where's the water coming from? This is not a water-covered, science fiction style water planet, is it? It's not a water-covered moon. So where's the water?
Well, Europa's a fascinating planet. It's definitely a fascinating moon. Around a fascinating planet, one can argue, actually.
Well, Jupiter is certainly its own episode, at least, minimum.
Indeed. So it has this saltwater ocean, which is underneath a really icy crust, which is on the surface. So it's super, super cold, right? It's minus 160 degrees on the surface.
Which is cold, yeah.
So this icy crust is something like 20 kilometres thick. Maybe the ocean is 100 to 200 kilometres deep underneath that.
And what's keeping the water? Is it pressure? Is it heat from the internal dynamics of the planet itself that's keeping the water rather than ice? We don't know.
Well, when planets and moons form, they have an internal heat source because you've crushed together a whole lot of matter, and that's really, really hot in the centre, and that's where most of Earth's heat comes from. Yeah. But Europa's way too small. It's lost all its initial primordial heat. And so what's happening now is that it happens to have a really, really, really big buddy that it's going around, which is Jupiter, which has an insane gravitational force on the moon, which is tugging it and pulling it and pushing it and squeezing it. And what that does is keeps a little bit of the interior of the planet warm.
Oh, right. Okay. And that heat keeps this huge ocean of salty water as liquid rather than just freezing to a huge chunk of ice.
Yeah. Really, really cold liquid.
Did we know that was there before the plumes were spotted?
Yeah, we did have a good idea of at least the outer composition of Europa. We have several missions, including the old Voyager probes went past Jupiter and its moons. And we've been able to measure from the gravitational field, from the magnetic field, actually what the composition is very roughly like. And that's always made us very excited about Europa. Because if you've got liquid water, that's one of your key ingredients for life.
Yes. Now, that's one of the really interesting things here, isn't it? And that's why this story and others like it will tend to get a lot of attention, both from scientists, but also particularly from the media. Because as soon as you start talking water, you start saying, could there be life? Could there be life? Could there be life on Europa?
Maybe. We know lots of really interesting things are happening. We know there's lots of geological processes. So when you look at something really, really old in the solar system, like let's say Mercury or the moon, you'll see it's got lots and lots of craters on the surface because over the course of time, lots of things have hit the surfaces of these objects and made the big dents that we see.
Same is true of Earth, of course, except that we have an atmosphere and we have oceans and things like that, and human beings these days who come along and wipe away the traces of anything big that's hit us. But if you know what you're looking for, you can find them. But on the moon, if something hits the moon and creates a crater, that tends to stick around until another crater wipes it out.
Yeah, so you look for processes that might be resurfacing a planet.
Right.
And Europa is almost a very smooth ball.
Right. Now, presumably it's like our own moon. It's being hit all the time. So what's making it so smooth is the question. So
there must be some of this liquid water that's underneath coming up to the surface in some form and refreezing, creating a nice smooth surface again.
So that's in some of the first looks at Europa, that would have been a bit of a giveaway, is, you find this incredibly smooth moon. There's some process here involving, presumably, something liquid smoothing out all of these bumps.
Yeah. And we even have some evidence of where that liquid might be coming up, because we can see huge cracks along the surface. So this crust isn't just like an eggshell that's impermeable. It's got, it's moving around a little bit like the tectonic plates on the surface of the Earth. And we can see that in between the cracks, you might have, areas which are more thermally active than others.
Cool. Okay. So there was a knowledge that there was water on Europa before. Is the interest in the plumes just simply further confirmation of that, or is there something else interesting about the plumes?
Well, the wonderful thing about the plumes is that means that there is water coming up to the surface, and not just the surface, the water is coming up into the atmosphere. Now, we thought that if we wanted to go and test the water below the ice, that we were going to have to drill down through this 20 kilometres worth of ice, which is a mammoth effort.
Well, for starters, it means you've actually got to be on the surface. You're not going to do that from a probe orbiting around it. So if we wanted to do that, we'd have to land on Europa. Not only that, but with something which is capable of drilling through 20 kilometres worth of ice.
Yeah,
which, let's face it, NASA, you're good and everything, but that's a tall order.
That's really, really hard.
Yeah.
So we thought, okay, well, maybe we can go to the cracks and see if there's any water coming up in these kind of areas. Maybe, but it still requires landing on the surface, which is a huge amount more difficult than just flying by, which is why we don't have so many landers in solar system exploration as flyby missions. But if we're getting this water up into the atmosphere, we can do something with the missions that fly by. We can have missions that will just sample this water and be able to test it on board without even landing on the surface of these planets.
So it can just sort of do the orbiter equivalent of just, sticking a cup out and gathering some of the stuff as you go past, bringing it in and taking a look at it. Because as you said before, when the Galileo mission went around, it wasn't looking for this. It was doing all sorts of other tests. It was looking down at the surface and looking at those, looking at magnetic fields and all sorts of things, but it wasn't thinking, let's stick the cup out the window and gather some stuff and pull it in and have a test. That was nowhere near the mission parameters. But if we wanted to go and do that, it's a hell of a lot easier than landing on the surface.
Yeah, which is super exciting, right? It means we've got an accessible way to test the water that is, well, at least been under the surface of the crust.
And presumably, if there is interesting stuff happening down there in these underground or under ice oceans, if there is life or just some really interesting chemistry going on, then some of that interesting chemistry is also being shot up into the atmosphere. You might collect water, but you might also collect all sorts of stuff, which could be really cool.
So we'd be looking for things like organic molecules, the building blocks essentially of life. Are there any amino acids? These really, really basic things. Because, let's face it, we're not looking for a civilization of ocean dwellers underneath the surface of Europa.
You're not going to find, the European equivalent of a wombat floating around in space having been shot out through a geyser. That's not going to happen. But tantalizing clues like amino acids and other really interesting biological chemistry. That's fascinating. So is this going to happen?
Well, hopefully. There's a couple of upcoming missions, one of which even last week they sort of knuckled down and said, right, we've got to get this funded now because it's so exciting. The first one is NASA's Europa Clipper. And this is kind of idea to launch in maybe 2022. So, a few years away yet to refine. But this is a specific plume-going mission. The idea
I like the sound of that, a plume-going mission. What do you work on? I work at NASA on a plume-going mission. Thank you very much. Put that on my CV.
Yep. So it's going to go direct to Europa, go fly through these plumes, maybe 40 times, something like that. and much, much lower than what Galileo did. So Galileo maybe got to 200 kilometres above the surface. These ones might go down to 25.
Right. Wow. Really close.
Yeah. So much, much more higher density for these plumes and, easier to measure, basically. So that's very exciting. And
that would be directly looking to gather and measure some of the material that is in the plume itself. It's not just measuring, magnetic fields and that sort of thing, that it's actually going, I'm going to stick the cup out the window and gather some of this stuff and test it.
Let's have a look at what those plumes are actually made of.
Cool.
Yeah. So literally last week after this announcement, I think the project scientists on that were like, right, we need to finish getting the funding for this mission because it's all go now.
Speaking of which, how about a little bit more funding for this thing?
Yeah. I mean, and there's another one that's coming up also, which is very exciting from ESA. It's one called JUICE. Do you want to have a go at what JUICE might stand for?
Okay. JUICE.
Yep.
So Jupiter. Ice.
Yeah.
Okay. Jupiter. Is there anything more to it? Because you could just have JU for Jupiter and ice for ice.
Oh, that's true. Yeah. Well, there is a little bit more, but it's not very obvious.
Go on then.
The Jupiter Icy Moon Explorer.
Of course it is. There you go. Thanks, guys. Juice. Looking forward to that one.
Not sure how they got the M in there, but yeah.
I don't know.
Astronomers are quite creative. And so again, that's a 2022 launch. And it's not just going to be for Europa. There's a few other moons it's going to visit. And again, up to 25 kilometres-ish off the surface. But I think both of those missions will be seriously influenced by the discovery in this paper. Yeah,
that's amazing. What about, you mentioned another moon around Saturn before, which has been observed to have the same kinds of plumes. Are we going there?
Enceladus. Yeah. Well, we've just been, actually. It's really, I mean, it was part of the incredibly successful Cassini mission. That's the one that had the Titan probe that landed on Titan.
Makes sense.
Yep, the Huygens probe. And Cassini itself, it lasted for ages. It took amazing pictures and it did these flybys.
Yeah, just stunning pictures of Saturn and the rings.
Yeah.
And the moons in the rings, and it's all good.
Yeah. So we're definitely going back, but I can't remember off the top of my head what the next one is.
Did that mission, did it go to look at the plumes? Did it take any samples? Did it manage to actually do any of that stuff? Or was it launched similarly, just too late?
I think they had some other instruments. I mean, it's obviously a later mission, so they had some more refined instruments, but the details of which I think would have to go and check, basically, to see what those instruments were.
Yeah. But this could be a whole new era of, let's go and just start sampling some, distant planet and distant moon.
Well, where we have done that, of course, is with comets.
Yes, we have. We even landed on a comet
a
couple of years ago, which was awesome.
Yeah. So we've flown through the tail of a comet and done kind of the same thing to look at questions like, is the water in comets the same as the water on Earth? Turns out it's not. But we can answer those kind of questions by doing these sample missions.
When you say, is the water on comets the same as water on Earth, what do you mean by that? Because water's water, right?
Well, we look at things called isotope ratios. So how much of this particular form of water compared to this particular form of water.
So when you say forms of water, just talk us through the isotope. Are you talking about the amount of different isotopes of hydrogen, for example?
Yeah. It's the chemical structures are slightly different, and what we were looking for is we have a particular chemical structure of how water exists in different ratios on Earth, and the idea was that did the water from Earth come from comets? Maybe it didn't, just land on Earth. Maybe it landed on Earth from these comets rather than being native, if you like, to our own planet.
But the fact that the water in the comets was seen to be different from the water on Earth suggests that wasn't the case, that it didn't come from the comets.
So far. But we've only been to one comet so far.
Well, again, N of one, more data needed. Move on. Yeah. Okay. So life on moons around Jupiter. I mean, that's exciting. You can completely understand why this is catching a few headlines. But as you said before, that's not going to be entire civilizations of beasties living under the ice. It's not going to be, European wombats. So what is it? What are we talking about when we talk about the potential for life elsewhere in the solar system?
Well, we're looking in the solar system and elsewhere, actually, for life as we know it. And there's a really good reason for that. It's because it's the easiest thing to study for us.
Yeah,
right?
We understand life on Earth pretty well, and it's all down at its basic root. it's all very, very similar. There's actually at its basis, there's not an enormous amount that differentiates us from trees and frogs and lice and that sort of thing. Like we're all the same stuff. And so let's start there. Start with the thing that we understand.
So whilst it's very, very plausible that life may arise in very exotic forms and very weird and wonderful environments, we're just looking for what we know first because that's easier. So we know that you might need some liquid water. That's all life on Earth pretty much needs some liquid water, some oxygen, some organic compounds, and some energy source. And we've mentioned most of those already. But if you're thinking about what life might be like under a 20-kilometre thick sheet of salty ice, it doesn't really sound particularly pleasant.
It doesn't. You'd kind of think, surely there's nothing could possibly survive. Nothing could thrive.
But one of the most
conditions.
Amazing things is we've found life on our own planet that survives in seemingly impossible conditions.
Like what?
Well, there's a whole class of organisms which are called extremophiles.
Oh, I like that.
Yeah. These are life forms.
So not just living in extreme environments, but filing in them, as in really, really getting off on living in extreme environments.
Absolutely loving it. Yeah. And you go to places in the bottoms of the oceans the pressures are huge. There's no sunlight at all because they're so deep. It can be very, very cold, or around things like thermal vents, it can be very, very hot. And we found things living there.
Life is amazing. Life will find a way, as they say in the classics. But it seems like, from what you're saying, life will find a way pretty much anywhere if the right building blocks are there. And there's, I'm guessing as long as there's a bit of an energy source of some kind, then as long as there's something that can feed in a bit of an impetus, then life will find a way.
A big revelation was you don't actually need to have the sun necessarily in these places. So yeah, it's really, really interesting. So there are these wonderful structures under the ocean called black smokers, and there's been life found in these black smokers, which are just almost impossible places.
What's a black? Is that a geological vent?
Yeah, a big plume, and it looks like it's smoking. And of course, it's underwater, so it's all liquid coming out. But really, really hot in the center. It's very, very cold outside of it, and yet
full of all sorts of horrific chemicals. I'm thinking.
Yeah.
There'd be a lot of sulfur and stuff in that.
Yeah, very acidic,
And yet there's some form of life that's going, yep, love that.
Yep.
Give me more of that.
So it's not such a stretch, actually, to think, well, if there were these maybe hydrothermal vents under the oceans on Europa, maybe there's life there.
Well, if there's enough energy to fling this stuff hundreds of kilometres up into space, or into the atmosphere of Europa, if there's enough energy from the gravitational tidal forces of Jupiter and so on to keep all the stuff liquid in the first place, then there's got to be something for life to cling on to, maybe, if there's the right conditions.
And some biologists have even thought about, well, what if there aren't these sort of plumes or smokers or whatever you want to call them? Maybe there's just processes that can take the heat from that tidal heating and just have life swimming around and on its own in the ocean.
So the kind of signatures that we'd be looking for in the plume as we fly past and stick the cup out the window, the various building blocks of life that we know here on Earth, as you say, you start with what you know. But then there's always the possibility that we might find a surprise. We might find a signature that we're not aware of. That's new.
Yeah. And the only way to do it is to go there and have a look.
Of course, the flip side to this is that there's a reasonably strong contingent of scientists who suspect that life on Earth didn't begin on Earth, that it came from somewhere else. There's a word for that, isn't there, which is escaping me at the moment.
It's called panspermia.
That's right. Pan meaning other and spermia meaning origin of life, I guess.
Yeah, spreading. And
yeah. Which means that life began somewhere else and came to Earth on a comet that crashed into us or in some other form, and that's where it all started. And so, looking for life as we know it in other places may not be so crazy. If we came from somewhere else, then maybe we'll find similar signatures somewhere
Yeah.
else. The thing I don't like about that theory is that it just shunts the whole where did life come from thing off into space somewhere. So, well, we don't have to worry about where it came from on Earth because it came from somewhere else. Good, excellent. Obvious follow-up question. Where did that one come from?
Yeah.
Yes.
Panspermia is an interesting one. It goes around in circles. My impression is that it's becoming a little bit less popular at the moment. I mean, who knows? But we are learning more and more about the evolution and origins of life on our own planet. And maybe it's possible that we didn't actually need a progenitor, if you like, coming from somewhere else. And maybe because we're not seeing the same things in comets as we see on the Earth, maybe that's something to do with the fact that we didn't have a huge influx of material from another place. But it's way too early to make that call.
I can't help but wonder what the global response, what the average person on the street's response would be to a final confirmation, if it ever comes. Yes, we have found, irrefutable evidence of life, as basic as it may be, elsewhere in the solar system or in the universe. It may be that is an incredible revelation for humanity, or it may be that we all just go, and then get on with our days and get back to eating our McDonald's and listening to it through our headphones, because we've come so far in the last couple of 100 years that would it be so surprising? Some people I think would be floored by it, but I think most of us would go, that's amazing. Anyway, what's on TV?
Yeah, it's hard because you almost expect it at this point. We've built it up and we've said, well, what if?
100 years ago, if we'd found, out of the blue, some irrefutable bit of evidence that may have been utterly, changing the entire world. But now, as you say, we're getting quite used to being one tiny dot in a vast universe.
I think you still have to think about it and just sit back in awe. I mean, there's no doubt in my mind it would be an ultimate game changer. It would be the ultimate scientific revolution, I think, in thinking, because it has so many other implications for philosophy, for theology, etc. So I can't see it being anything other than probably one of the greatest discoveries we'd ever make.
I agree. I don't know. We could have an entire episode on the ramifications of this, and we're not going to know until we know. But I kind of feel a little bit like maybe we've already sort of jumped over that one into, okay, all right, makes sense, sure. Anyway, we'll leave that for should it ever happen. A little bit more on how this discovery came about. So going back to what you were saying before about how these scientists looked back at old data that was sitting on the shelf from the Galileo mission and managed to look back through it and figure out from the data that was there, that was never intended to be looked at in this way, but find evidence for these plumes and actually be able to learn something about it. But you said something tantalizing back in that conversation, which was that the modeling techniques have improved to allow us to do that. Tell me more about that.
Yeah, well, this is one of these lovely stories of science as well. I mean, we always have this interplay between data, between theory, and between the models that we can construct. And it's a cyclical thing. So you go around and we collected the data, we used our current models, etc. And then in that intervening 20 years since that data were collected, we have developed those models and those theories much, much further. So this is the models that we're using as a branch of something called MHD.
Okay.
Which is called magnetohydrodynamics.
Right.
And
so magnetism, hydro, water, dynamics, moving about.
Yeah. So we're marrying up together electromagnetic stuff, so electricity, magnetism, and then we're throwing in, just for good measure, fluid dynamics. Now, these are all independently really difficult things to understand. Putting them together, I mean, MHD is widely regarded as one of the most complex topics in physics to understand, let alone astrophysics.
Cool. So let's do it for a moon a really long way away.
Yeah, why not?
What the hell?
It's all to do with plasmas. Okay, so these are, we're talking about the atmospheres of these planets that have charged particles like electrons running around in the atmosphere. So it's not like a solid, liquid or gas. It's this plasma which has charged particles in it. And those charged particles interact with magnetic fields, and you get this electromagnetism, and then you get the fluid motion of the atmosphere as well. It's super hard. I have to stress.
It
is
sounds
so
it,
hard.
I have to say. It sounds it.
Yeah. We now have three-dimensional MHD models of how atmospheres would react when one of these plumes goes up into them. And that's what they were able to apply to see, okay, well, what would this particular satellite detect if one of these things happened? And when you go and look at the data in the Nature paper, the model fit next to the data is just beautiful. It almost fits exactly.
That's one of those things in science which, until you experience it, you can't quite describe the little shiver that goes up your spine when your data matches your model so well. But that is absolutely fascinating, because you need reminding every once in a while that, of course, a scientific measurement like is happening on the Galileo probe is nothing without some framework of understanding around it. And in science, we typically call that the theory, and in particular the models that put together a whole bunch of bits of theory and assumptions and expectations together into, if this were the case, then what would it look like? And as you say, those have developed over 20 years to the point where we can work backwards and say, what would we have seen? Let's go and have a look at that. And that's really cool.
Yeah, so the modern astronomer is not just a stamp collector saying, well, we found this thing and it's quite interesting. We found this star, we found this planet, we found this galaxy. We want to understand it, and we need that physics and the models and everything has to come together in order for us to actually develop that understanding thoroughly.
That is one of the awesome things about modern astronomy, is that it's got room for pretty much anyone. You need the computer scientists, you need the data people who just really want to get their hands dirty on the data. You need the technicians to be able to build the instruments and test the instruments. You need the theoreticians who love getting their hands dirty with a lot of maths. You've got room for so many different kinds of people. It's not looking through the eyepiece of a telescope by so many orders of magnitude. It's a great subject.
It's a wonderful interdisciplinary science, yeah. And I think the wonderful thing about modern astronomy is the quantity of data that we are getting and have been getting for some time. And this is, I think, quite central to this story. We're able to use data from 20 years ago. Now that's sort of, okay, fine, it doesn't sound like a big deal. But imagine what your computer looked like 20 years ago.
Okay, so we're talking back in the late 90s. So I had one of the very early iMacs. I seem to remember it was sort of lime green in colour, and has probably about a tenth the power of the phone in my pocket right now.
Maybe even less.
Yeah.
I remember when a gigabyte was an enormously overwhelming amount of data.
I know. Giga means billion. That's a lot. That's a lot of bytes. Yeah, and now it's just, that's a small fraction of our music collection.
Yeah. So this is a little bit about the history of data and data curatorship and why that's so important. I mean, astronomy isn't arguably the oldest science, however you want to take that. But definitely we've been making measurements for hundreds of years. We have drawings from the very, very early astronomers who looked through telescopes and drew things, and there's information that can be got from those. We have photographic plates. Astronomers were very early adopters of photography. They thought, that's wonderful. Let's start exposing huge, almost half a square metre in some cases of photographic plates.
And then they used to, didn't they? You used to get a couple of different exposures and be just flipping backwards and forwards between them by eye, looking for tiny changes in a single dot on that photographic plate, which is nuts.
Yeah, and those plates are still important because that's a snapshot of this night sky at that particular
time. You can't, that's the one thing you can't go back and do. You can't go back and take those pictures again. Yeah. So the ones we've got are really important.
And then coming into the 20th century, we started to use early versions of computers. We had the old punch cards. We had, I remember seeing from my supervisor actually, a dot matrix printout of a spectrum of a star.
Oh,
and
fabulous.
it was about 30 or 40 centimeters high of just folded of the old dot matrix paper. And you had to it would have been meters and meters and meters long if you unrolled this whole thing.
I'm amazed that they managed to get that much paper through it without the little holes on the side screwing up and the thing going off at an angle and it all ending up in a big tangled mess. That always happened to me.
Yeah.
But yeah, you've got those.
Yeah.
You've got however many, probably hundreds of different digital file types now.
Yep.
It's hard enough going back and opening up a Microsoft Word document from 15 years ago on a modern computer, let alone just the sheer variety of different data types that there must be from astronomy over the last several decades. But it's all out there, and it's, as this story shows, it can be incredibly important.
Yeah. And so we've got to look after our data, actually. And even digital data, you can think, oh, well, it's all stored on a hard drive or a server somewhere. It's up in the cloud. It's fine. Actually, that still needs some care and attention to look after it.
A lot of care and attention. You go and look at some of these cloud-based storage systems, even just for your home computer backup. They have hard drives failing constantly. They need to have this constant turnover. Yeah, the curation and the looking after this data, because it disappears, it dies, CDs wear out, tapes get demagnetized or lost. These things happen.
Yeah. And we need to keep updating the interfaces that we use to use that data. So even the portals, if you like, for the little search engines that we say, I want to get all the data on this particular object, even those need updating as computers and software and technology develops. So we, as astronomers and scientists, I think in general, have to be very, very careful about how we look after our data, because there are definitely hidden gems in there, and we will keep constantly going back to find them.
You never know what you're going to find. And that's it for another episode of Syzygy. Once again, if you've enjoyed what you've listened to, then you really should tell us and the world about that. We'd really appreciate it if you go to your podcast directory of choice, iTunes or whichever one you're using, and leave us a review. Hit us up for some stars. Tell us what you think. Obviously, if you really enjoy it, then that'd be great. If you think it's, not the world's greatest podcast, keep that to yourself. But if you're enjoying it, then give us a review. The reason we ask you to do that is because it actually really helps. It helps other people to find us and share the love of the universe, share the love of astronomy. Other ways that you can get in touch with us, we'd love you to send through your comments, your thoughts, and particularly questions. If you send through a question, then we may well feature it on a future episode of the podcast. You can do that by getting in contact with us through our website, syzygy.fm, syzygy.fm, or you can contact us on Twitter, can't they, Emily?
At SYZYGYPOD, Syzygy Pod.
Syzygy Pod. So go and hit us up on Twitter, and we might have a little bit of conversation. Send us a question. We'll keep an eye out for that one. But otherwise, that's it for this episode. So we'll catch you next time for another fabulous story of the cosmos on Syzygy. But until then, bye for now.
Bye.
It's always the way. I'm going to sneeze. I'm going to sneeze. I'm going to sneeze. I'm not going to sneeze.
No, I'm just going to start crying.
Do you need a minute? Are you okay?
No, I'm okay.